All right, well, welcome to another fun-filled day of Math 202. Our plan today is to kind of pick up where we left off. We've been talking about curvature, so we're still going to continue that. I've introduced you to big T and big N. I'm going to introduce you to another vector called big B, which is related to these guys as well. We'll talk about these best fit circles to curves and how curvature is related to them. So we'll kind of wrap all that up, and then we'll start talking about actually using this, specifically with accelerations and how we can determine from an acceleration vector how much is pointing in the centripetal direction, right, in the direction of big N, so that we know basically what's causing a change in direction, and then also find the tangential acceleration, what part is changing speed. So anyway, so that's our plan. That's where we're going to be. So let me start off like always. Are there any questions regarding the homework? Anything we want to look at?
Yes. I'll just type it.
Okay, so Evan, you say 6. Can you give me a section, please? Okay, from 3.3, got it. All right, and was that you, Seamus, that said you were going to type it in?
Yes.
You're working on it? Okay. That's cool. So what I'm going to do then is let's go look at the one that Evan put up first while you're figuring out the one that you want to see there, Seamus, or typing it in. So let me go ahead and share my screen with you guys. And we'll go find it. So right now you're seeing my first year calculus class, which is going to do us no good whatsoever. My computer is acting like I feel right now. All right, we're almost there. All right. So we'll go take a look at number 6. I know, Evan, you said either one is fine, but since you started with 6 as your first question, let's go ahead and look at that. So what we've got here says, consider the space curve r equals 2 sine t, 2 cosine t, t. Anybody recognize what kind of shape that is?
A helix?
Yeah, that's just a helix. What's the 2 do?
It's the radius, right?
Yeah, that's exactly right. So it just made it a helix. It's got a bigger radius than the unit circle. So we've seen things like this. This is just a bigger helix. But what we want to do, 2 things. One, we want to find the arc length function. So we want to be able to describe the path that we've traveled in terms of t, in terms of our t variable. And then for the second part, for this, what we want to do is then replace the t's with s's so that we can parameterize this function in terms of arc length. So we know where we are after we've traveled a certain distance. Okay, so let me go ahead and pull up a whiteboard here. So, there we go. All right, so we got our whiteboard. So let's just start with that function. So we had r equals 2 cosine t, 2 sine t, t. Okay, so how do we get the arc length function? Okay, so Victor just put in integral of the magnitude of r prime. Yeah, so in general, you want to find your arc length, s of t. It's the integral from somewhere to t. We'll go ahead and call it 0 to t. And we're going to take the magnitude of r prime du. We'll put in a little dummy variable. All right, so for this one, it's going to be integral from 0 to t of the square root of, well, the derivative of 2 cosine is a minus 2 sine t that we're going to square. Oops, except that should be a u. Sorry about that. Hold on a second. Minus 2 sine u squared plus 2 cosine of u squared plus 1 squared. And that's all du. Whoa, goodness gracious, what was that? Stop. My stylus has taken on a mind of its own. I'm pretty sure that's how Skynet starts. First it takes over your stylus, then it starts creating killing machines. So you guys have been warned. You saw it happen here first. And now it won't even let me do the stupid draw tool. There we go. Okay. All right, so we just need to integrate this. Well, we can simplify this a little bit, right? This is going to be the square root of 4 sine squared plus 4 cosine squared plus 1. And of course, 4 sine squared plus 4 cosine squared is 4. So this ends up being the integral from 0 to t of the square root of 5 du. So helixes are nice. One of the reasons we tend to see these as examples is that their arc lengths end up being nice and simple. So it's easy to change these from t's to s's. All right, so now when we integrate this, of course, since it's just root 5, we get root 5t. So that's what's going to go in the first box, right? Remember that there were 2 things that we had to fill out for this homework set. The first one said s of t equals, well, it's our root 5 times t. So what's nice about this formula, other than the fact that we're going to be able to use it to parameterize in terms of s instead of t, is that we now have a way of knowing how far we traveled given a certain amount of time, right? So basically this is saying every one time period we're going root 5 lengths, whatever that happens to be. So every hour we're doing root 5 miles, or every second we're doing root 5 meters, or however you want to think about it. So interestingly enough, with this function, if this is actually describing the path of a particle, the particle has constant speed. And that speed is root 5. All right, so now for the second part, it says we want to parameterize in terms of s. So we're just going to solve this for t. So t is equal to s over the square root of 5. And now if we just fire that up in here for all the different t's, we can get r as a function of s. And it's now 2 cosine of s over root 5, comma, 2 sine s over root 5, comma, I ran out of space, so I'm going to do it down here. Just make sure. That third component, t, is just going to be s over root 5. And that's the process, always. It's just a matter of doing this integral first so that you can find the relationship between s and t, and then solving for t. All right, so does that help with this one? Does that make a little more sense? Hearing nothing, I'm going to go with yep. Okay, so yeah, this one actually is pretty easy. I want you see where to go with it. So let's actually go take a look at the other one. And then we'll hit Seamus's questions. So let's see, 7. Right, very similar idea. Just this time, obviously, what we're going to be integrating is a little bit different. So let me at least just get us kind of started. So you're going to start by finding your R prime, right? So let me go ahead and go to a whiteboard again. So let's clear what we've got so far. But now this one, we've got a different R, right? R was 2t minus 5, 5t plus 5, and minus 5t minus 5. And this one actually is going to be even easier because when we find R prime, notice that it's a constant function. So finding the magnitude of R prime is pretty trivial, right? It's 4 plus 25 plus 25, which is the square root of 54. And so if we integrate that, from here you can see that it's going to play out exactly like the other one, right? So both of these are kind of nice, and obviously with the homeworks we're not going to give you something that's got a really terrible thing to integrate, because otherwise we're screwed from the start. All right, so good for that one. All right, awesome. So the other ones that were of interest were the, James said from 14 onward.
Yeah,
So,
question 14, and this is when it starts to be just two variables. And
okay.
that might be why I'm slipping up, but I'm really confused, so I'm just getting every single one of these wrong.
Okay, let's go find number 14 here. I'm just going to tell you guys, like I just saw here for number 18, like we haven't talked about a binormal vector. So some of this stuff we may not have, I may not have actually shown you the better ways of doing it. Right? But let's just see what we got. Okay, so find the curvature of R equals t minus sine t, 1 minus cosine t. All right, so that's easy enough. I'm just writing it down so I can reference it. So let's go to the whiteboard and do this again. All right, so this time R is t minus sine t, comma, 1 minus cosine t. Now, it did ask us to find curvature. And with curvature, we have lots of different options.
Yeah, so I'm going with the dt over t, the magnitude of that over the magnitude of R prime.
Okay.
I got root 2 for the magnitude of R prime.
Okay.
Is that true?
Let me just pause you here for a second, because we had a whole bunch of different forms for curvature. I actually recommend using the one that involve the R prime cross R double prime.
So I don't fully understand how to do a cross product with two variables.
Okay, well then let me show you. Okay, so what we've got going on here then is we need R prime and R double prime, right? So R prime is no big deal. It's just 1 minus cosine, and then sine. And then r double prime is going to be sine cosine. All right, now we do need to do r prime cross r double prime, but we're only in 2 components, and we know for cross products we need to be in the third, or have a third component. So does anybody remember how we kind of fake this out?
Don't we just add a 0?
We totally do. We just put a 0 in our z coordinate, so you can just imagine it's this. Let me erase those guys. So these are the same vectors. These are still 2D vectors. We're just saying that the z coordinate is 0, so they're in the 2D world. But now we can actually find the cross product. So when we cross this, you can get sine times 0 minus 0 times cosine, so that's 0. For the I, you're going to get 0 times sine minus 1 minus cosine times 0, so that's also 0. And then for the z, the k, you're going to get cosine times 1 minus cosine, so cosine minus cosine squared, minus sine squared. And we can even simplify that a little bit to just cosine of t minus 1.
Would it be cosine? Oh, wait, never mind. It's a positive. No, sorry.
Those are my favorite questions, the one that Jacob answers for himself. All right, so there's our r prime cross r double prime. Now, the fact that it has zeros in these 2 components should not surprise you whatsoever. Because remember what happens when we get a cross product of 2, we get a vector that's perpendicular to these. Well, these 2, r prime and r double prime, are in the 2D world. They both lie in the xy plane. And so the only thing that's going to be orthogonal to both of those is something that points in the z direction. And so that's this vector, 0, 0, and then this guy. It just happens that it ends up being cosine of t minus 1, just because, right? But the fact that it points in that direction is exactly what we want. All right, so before I continue, does that at least help answer the how we deal with 2D vectors if we're going to cross them, Shannon?
Yeah, I guess I can just start employing that strategy for the rest of these 2D vectors.
I highly recommend it, because now think about what that curvature formula is, right? It's the magnitude of r prime cross r double prime. And then you guys remember what goes on the bottom?
The magnitude of the cross product vector.
The magnitude of the cross product vector goes on the top.
Oh, the magnitude of the normal vector without the primes.
So the magnitude of r and then a cube. Is that right?
Yeah, magnitude of r prime cubed.
Okay, so it's the magnitude of r prime cubed. All right, so there's our curvature. So now this can be pretty fast, because the magnitude of the r prime cross r double prime, since it just points in one direction, that's just cosine t minus 1. And then the magnitude of r prime would be the square root of 1 minus cosine t squared plus sine squared, that we would then cube. Right, and we could simplify that down, obviously, and then go from there. But finding the curvature formula is much faster, I think, in this way, if you're given an r. Now, they did specifically ask us to figure this out when I think it said t equals pi. So when you're actually given a location, so you're given a t value, what I do is I actually plug this in before I use the formula. So basically r prime of pi, if I use that formula, cosine of pi is -1. So I get 2, sine of pi is 0. So there's my r prime. And then r prime cross r double prime, it's going to be 0, 0. Again, cosine of pi is -1, so that's -2. And check out how fast this is then to use the curvature formula. It's the magnitude of r prime cross r double prime. Cool, -2. Except it's the magnitude, so it's a positive number. And then that's divided by r prime cubed. So there you go. That's the curvature of this thing at t equals pi. So if you're
Wow.
going to, no, go ahead.
For why is it where it says k equals, magnitude of r prime cross r double prime?
Yeah.
Why is it equal to cosine of t minus 1? Why is it not cosine t minus 1 squared with square? Oh, wait, never mind. Never mind.
Man, that
Never
was a
mind.
Jacob question. All right.
Yeah.
No, that's all good. And technically, I should have absolute values around this because it is possible that cosine of t minus 1 is negative and curvature needs to be a positive. But anytime you have a vector that just has one component, the magnitude is its absolute value. Right, because kind of like what Bradley was talking through, right? And he's like, well, shouldn't it be the square root of that thing squared? And we all know that when you take the square root of a square, you get what you started with. So save yourself some time and just jump straight to the, well, it's just whatever that one is. All right, so is that better for this one, number 14?
Yes, and that definitely just answers my question on the rest of them, because I'm sure that if I just employ this strategy, then I'll be fine.
Okay. And then I just want to mention, if you look in the chat window, you'll see that Vector put something about finding the curvature using the absolute value of y double prime divided by the square root of, or well, basically 1 plus y prime raised to the 3/2, y prime squared. There is another formula for curvature. I haven't shown it to you yet. That's the first thing we're going to do today is talk about that. And that's how you find curvature if you're given a function just y equals f of x, right? So like if you have something that's just y equals f of x, excuse me, maybe you want to find the curvature of it, but you don't want to bother trying to find some sort of a vector valued function. There is a formula to do that, and that's what Vector had put into the chat box. But in this case, I still would avoid it because it would require eliminating the parameter, getting this thing just as a function of y and x. And I really don't want to do that. Like the whole point of having these multiple forms is to find the one that's fastest and easiest to actually do the curvature. And in this case, since it's already in that vector valued form, it's probably fastest to use the r prime cross r double prime deal.
What do you recommend as far as like which form to use? Because
Well,
I think
let me finish showing you the this last form, and then once we have all the different forms for curvature, I can maybe talk through a little bit better of when I use which one, and kind of address that question. So if you don't mind just holding off on that for just a minute, Bradley, I will definitely hit that.
sounds good.
Okay. All right, so any other questions on homework at this point? Or are we kind of in an okay spot? I mean, I know that homework's not due now again until Monday, so some of you are probably not even thinking about it yet. But thanks for those of you who did have questions. All right, well then let me go ahead and hop to the whiteboard and we will continue our discussion of curvature. So just give me 1 second. All right, so hopefully everybody can now see the whiteboard and hear me all right. Just give me a quick thumbs up if you hear me. All right, thank you guys. All right, so let's continue our discussion of curvature, and we'll even begin with what the definition was, right? And then the various formulas that we ended up getting for it. So if we just start with definition of curvature, where it came from, it's K, right? But really we were looking at what is the change in the normal or of the tangent vector with respect to arc length. So it was the magnitude of dt ds. So remember that S is arc length. And so what we're doing here is we're just basically saying what's happening to that tangent vector as we're moving along the curve. If it has a very quick change over a short distance, curvature is greater. If there's not a lot of change over a longer distance, then the curvature is smaller, right? So this was how it was actually defined. In terms of the values, right, k equals 0, this means that it's straight, meaning it's linear. Okay, so if you've got a line, by definition, a line will have a curvature of 0 because the tangent vector never changes. Okay, so lines have 0 curvature, and you can end up getting 0 curvature somewhere along the way in a function that's not a line. It just means locally at that point it's linear. Okay, so that's k equals 0, and then bigger K means sharper turn. So if you think about it as like a road, those really tight corners where you have to really slow down because you got like a big hairpin turn, like driving down Kingsbury down to Minden and Gardnerville. If you've ever been on that road, you know exactly what I'm talking about. There are a couple of places where you got those big hairpins. Those have great K. They have really large K, as opposed to those nice big winding curves have a smaller K. Okay, so K goes from 0. I'm sorry?
So like comparing Spooner to Kingsbury, Kingsbury has a larger K pretty much more of the time.
Correct. Yeah. So Spooner, while curvy, is not nearly as curvy as Kingsbury. So I don't think, I'm just trying to picture the drive, and I can't think of anywhere along Highway 50 on the Nevada side that has a curvature that rivals spots on Kingsbury.
Me neither.
Think about going up to the top of Kingsbury. There are a couple of those places where you get those really sharp turns, like the one near the top before you turn off to go on North Benjamin to the Tahoe Rim Trail, right? That's going to have super big K. You will never see anything like that on Spooner. So yeah, that's a really good way of thinking about it. And for those of you who have no idea what we're talking about, these are roads in Tahoe. And when you live in a mountain town, you are very familiar with this idea of curvature, for sure. All right. Anyway, so this was definition. Now, we did develop a couple of other forms for this, right? I think if I recall correctly, where we had gotten as a group is we had 3 forms, right? And so we had this one, the original definition, but then we saw that it wasn't always practical to try to differentiate when you're in terms of arc length. And so we saw, well, what if we convert it to t, to the original parameter t, and that gave us this second form. And the second form was, and I think this was what, I forget who it was, suggested that we start with this one. But it was this, excuse me, where we actually have the derivative of t, its magnitude, divided by the derivative of r. Right, and so we saw where this came from. We actually developed where it came from. It's actually a pretty quick proof, but this was a second option. And then I gave you the third one, the one that we just used, and I gave this to you without proof. And it looks like this. So it's the magnitude of r prime cross r double prime divided by the magnitude of r prime cubed. All right, so this is where we had gotten ourselves to. That we have 3 options so far for curvature. And they're all equally valid, right? Like when we did that homework problem and I went with this third one, we could have just as easily gone with the second one or the first one. It would have given us the same number. Like we ended up with 1/4. It's going to be 1/4 regardless of which of these we use. It's just a question of which of these is going to be easiest to find, right? And that was, I think, the crux of Bradley's question, which I'll get to once I give you the fourth one. Okay, so we're going to have one more in here. So if we keep doing our list of ors, let's save a spot for a fourth one. But this fourth one is going to be when we have a plane curve. And plane, I don't mean like boring. I mean in the xy plane. All right. So basically, this is what if we have y equals f of x. Because that happens to us all the time, right? I mean, think about coming up through math until you met vector valued function. You did everything like this. And there are plenty of times that we have things that are just 2-dimensional and not 3-dimensional. So how do we go about finding this? All right, well, we're going to build it, basically. We're going to build it by thinking about these as vector valued functions. Okay, so what I want to do is I want to create an R for this. So here's what we're going to do. If y is equal to f of x, I'm going to create R this way. I'm going to make the x component t. So basically, x is equal to t. I'm just changing the name. So my y then is going to be f of t. And my z is going to be 0. So before we move on, I just want to make sure everybody's cool with how I built that. So the z is 0 because we're in the plane. And really my parameterization is I'm just letting y equal or x equal t. That's my conversion here. If you remember the first time you saw parametric equations, and we ever had parameterize a function, this is the most basic and simplest way to do that. You just let x equal t and then everything spills. Okay, so we're going to take this and we're going to apply the third form, the one that we just used. And we'll see what that creates for the curvature. So we need r prime and r double prime. So r prime is 1, comma, f prime, comma 0. And then r double prime is 0, f double prime, 0. So I'm just differentiating with respect to t, but there's my r prime and my r double prime. So now let's use our formula. Let's find r prime cross r double prime. Let's get its magnitude and then do the same thing on the bottom. Let's get the magnitude of r prime, and then that will give us this third formula. All right, so r prime cross r double prime, I've already kind of got it set up here. So for the i's, I'm going to get 0 minus 0. For the j's, I'm also going to get 0. And then for the k's, I'm going to get 1 times f double prime minus 0 times f prime. So it's just f double prime. So the cross product vector here, just like with that other example, is only in the z direction because it has to be orthogonal to the others, which are in the xy plane. And its component is f double prime. if you just kind of stop and think about that for a second, isn't that sort of beautiful? That this cross product, this normal vector, is actually just the second derivative pointing up. I find that kind of pretty.
Is that the case always?
Yeah. If we define our curve parametrically with x equals t, this is always what it is, yeah. All right, so now magnitude of r prime, and then just we'll be done, right? So the magnitude of r prime cross r double prime, well, it's going to be, since we're in the just a one component vector, it's going to be the absolute value of f double prime. So if it's negative, we just make it positive, but it's its absolute value. And then the magnitude of r prime, that's the other piece we need. Well, if we jump back up here, that's the square root of 1 plus f prime of t. And that f prime of t, of course, is squared. Right? And then plus 0, but we obviously don't worry about that. All right, so we'll put this together, and that's going to give us our curvature. So if we've got a plane curve, a good old y equals f of x, then the curvature of this is going to be the absolute value of y double prime divided by the square root of 1 plus y prime squared. So we'll go ahead and put a box around that. And that's our fourth way of being able to calculate a curvature. So again, if you go back and you look at the chat box, this is what Vector put in there. And probably, I don't want to put words into your mouth here, but I'm going to guess that you wanted to do that because you recognize that this was a curve in 2 dimensions. And so this applies to 2 dimensions.
So that last one only applies to 2-dimensional curves.
It's got to be a curve that's in the xy plane.
Gotcha.
That we would write equals f of x. Okay, so let me actually show you how fast this is when you're in this situation where you've got a function that is in 2D. All right, so I don't know if I'm going to try to avoid the glare here, but let's just say we've got y equals x squared. And that did not work. Let me drop it a little bit further. Okay, so y equals x squared. You all know it. You love it. It's a great function. No big deal. So if you want to find the curvature, all you need are the derivative and the second derivative. Okay, well, that's easy enough. Y prime is 2x. Y double prime is 2. So what we end up getting then for the curvature of the parabola is the absolute value of y double prime. So that's just 2 on top, divided by the square root of 1 plus the derivative squared. So that's 1 plus 4x squared. And the reason that this is nice, like we'll go ahead and just kind of circle that, is now if you want to know what the curvature is, all you have to do is plug in your x value. What's your curvature? I don't know, where? Well, how about at the origin? Okay, plug in x equals 0, curvature is 2. Well, what if you're out at x equals 3? Okay, well, 3 times 3 is 9, times 4 is 36, plus 1 is 37. Curvature is 2 over root 37. So this is actually really, really nice when you're in a situation of just a regular old function that you know and love.
I have a quick question.
Yeah, it's super. Oh, yeah, for it.
So suppose in an applied sense, when we're asking curvature, would there be units associated with it? in an applied
Oh,
sense?
very good question. No, curvature is actually dimensionless. It's dimensionless. But check this out. So you know x squared, it's good old parabola. So let's think about curvature. What point on this is going to have greatest curvature?
Are there ways to measure curvature that have units for like engineering or something like that?
No, it's dimensionless.
Okay.
But like the way you would measure it is you would go out and you would plot your curve and then, you know, try to fit a function to it. I mean,
Okay.
at least that's all I know of. I mean, there may be engineers like people that design roadways and stuff may have alternate ways, but I don't know. But and you guys know my background has zero to do with engineering, so you know I can't think of a scientific reason that you would actually or a scientific example that you would do this where you could actually go out and measure, because most of the time you're going to worry about this in honestly like in cosmology, right? Astrophysics. Think
Yeah.
of like paths of comets or you know probes we're sending to places and their curvature might matter. Um, it's not like you're going to be able to go out there and do
Measure the
measurements.
path of the probe. Yeah. All right.
I mean, I don't know. Maybe you are that good, right? Maybe you've got like the Iron Man suit, and so you can cruise out there or something. You know, more power to you. If you do, I'm a little jealous you haven't shared it with me yet, but that's okay. We can work out something. But looking at this parabola, what part of it has greatest curvature? Which part of it is least straight? All right, so Eduardo was saying x equals
Think about
0. So yeah,
origin. Yeah.
at the vertex, right? The vertex of
Yeah.
this thing where it's tightest. As you start moving away, it starts looking more and more straight, right? Well, look at this formula for curvature. It's going to be greatest when the denominator is smallest, and this is going to be smallest when x is equal to 0. As x progresses, as x goes towards infinity, this bottom grows. It grows without bound, which then means that this whole fraction drops off to 0. And so it's exactly describing what we see. The parabola is most curvy at the vertex, and as we move away, it gets straighter and straighter. Right? So if you go far enough out there, it's going to look completely straight because this curvature number is going to be so small. And you don't really have to go very far for it to get tiny. Right? Let's just think about going out to 10. So if we go to x equals 10, 10 squared is 100. This is 401. That's close enough to 400. Square root of 400 is 20. 2 over 20 is 1/10. So at x equals 10, the curvature is about 0.1, which is pretty small, right? It's getting close to 0. And we didn't really even have to go out that far yet. Imagine going out to x equals 1,000,000. Okay, well, 1,000,000 squared. So 4 times 1,000,000 squared, the square root of that's about 2 times 1,000,000. It's 1 over 1,000,000th. So at x equals 1,000,000, your curvature is around 1 over 1,000,000. 0.05 zeros and a 1, right? I mean, it's tiny, 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 tiny. So you don't really have to go out very far for this parabola to start looking flat. But you can imagine that other things, it's even quicker than a parabola. Others, it's just very bendy always. Like, let's do one more. Since this formula is pretty fast, right? You saw how quick this was. Let's do another one.
Just a quick question.
Sure, go for it.
In the formula that we derive, it shouldn't be in the denominator the square root to the third.
Oh, you are right. Thank you for catching that.
Okay.
Okay, well, that makes it so that it gets flatter even faster. But yeah, thank you. I was all excited I forgot that cube. All right, so let me show you another one. And this is another function that you know and love. Well, maybe not love, but you know it pretty well. For those of you who know me, this is one of my favorites. Let's look at cosine. Now, you know enough about cosine that if we're going to talk about curvature, we should expect that the curvature is cyclical, right? We should be going from points of greater curvature to less curvature to greater curvature to less curvature, depending upon where we are in that sine wave. But let's look at what the formula actually gives us. So we need y prime, which is negative sine, and y double prime, which is negative cosine. So our curvature is going to be the absolute value of cosine of x. Hopefully you guys are good with me dropping the minus sign since we've got our absolute values. Divided by the square root of 1 plus sine squared x cubed. So there's your formula for curvature, regardless of where you are. So let's look at a graph of cosine and just kind of talk about greater curvature, less curvature, and so on. First, I want you to notice that this sometimes equals 0. Unlike the one that was y equals x squared, with the cosine, there are going to be times where we get 0 curvature. Meaning there are times where this is perfectly straight, perfectly linear, right? And that's going to be where cosine is equal to 0. So Vector just put in pi over 2. That's definitely one of them, but also 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. And then notice that curvature is going to be changing with sines and cosines, but it's going to max out when cosine is plus or minus 1, because that makes the top biggest and also makes the bottom smallest, because that's when sine is plus or is 0. And so that's at 0, pi, 2 pi, and so on. So think about the graph of cosine. We just saw that k is equal to 0 at the half pi's. So pi over 2, 3 pi over 2, 5 pi over 2, and so on. Well, that's, I didn't draw this very well because those need to be the intercepts. Hold on one second. Let me make this a little bit better. That's closer. That's closer to actual cosine. So here is pi over 2, 3 pi over 2, 5 pi over 2, minus pi over 2, minus 3 pi over 2. And you can see that at those spots, it's pretty much linear. I mean, you zoom in here, it's going to look nice and straight. We were getting maximum curvature when cosine was plus or minus 1, which is these points, the tops and the bottoms. And in fact, if you want to know exactly what the maximum curvature is, let's plug in, say, 0. If you plug in x equals 0, sine is 0, so the bottom is 1. The top is 1. So we're going to get a k value of 1 when we're at the peaks and the troughs. When we're at those intercepts, we're going to get k equals 0. And so for cosine, its curvature is bounded between 0 and 1. It'll never be anything more than 1. And it's also very regular, right? It goes from 0 to 1, back to 0, back to 1, back to 0, back to 1, because of the periodic nature of cosine. So it's kind of nice that this real simple way of defining curvature as a, this is how the function's tangent vector is changing as we move along the path, the arc length. even in all these other forms, still are getting at what we want it to be. Curvature of 0 means that it's straight. The bigger the k, the more curvy it happens to be. All right, so how are we doing with this fourth one? Makes sense where it came from? You can see that it's not too difficult to use. I'm getting some thumbs up. Okay, so let me address Bradley's question. And then after we do that, let's actually talk about what a curvature number means. So like when we get a curvature of 1, what does that mean as opposed to a curvature of 1, 4, like we found in that homework question you guys asked and all that, right? What do those actual curvatures mean? I can tell you that as well, but let's hold off on that for just 1 second. Let me start with Bradley's question of how do you pick which form? Okay, the first one, the one that we use as definition, I only ever use that. I only ever use this first one if I've got my function in terms of s. So if it's already parameterized in terms of arc length, then I'll use that first one. If I don't already have that, I jump to something else. So this is very rare, this first one. It's very rare that I use that guy because it's not often that we have things parameterized in terms of distance traveled. They're usually more parameterized in terms of time interval passed, right? That is passed. Okay, so very, very rare do I use that first one. Okay, so then the next question is, what about number 2 and number 3? Because number 2 and number 3 are pretty similar, and they both come from knowing r as a function of t. So which one of these do I do? Well, honestly, that usually depends on what the component functions look like. Because think about t prime. I got to find t prime, right? Finding t, I got to take a derivative of r and get its magnitude. I'm going to have to do that anyway, right? So that's a wash. Creating t, that's not a big deal. But then I have to differentiate t. And that can get really ugly really fast, right? I mean, I've even shown you some examples where I've punted in the middle and gone, well, now you differentiate and I do the hand waving thing. So what really restricts this one is finding t prime. So what I'll do is I'll start by finding r prime and its magnitude because I need them anyway. And at that point, I visualize what big T looks like. And I envision what it's going to take to differentiate it. If it's going to take me much work, I immediately pass on it. Okay, so that's what determines that. Because this one, the one that we used for that homework problem, this one, really the difficulty is in doing the cross product. Because finding r prime, we already had to do that anyway. Finding an r double prime, that's usually not that much worse. Right? And then it just comes down to doing cross product. Me personally, I'm very comfortable with cross products. So I don't hesitate with this one. It's kind of nice. It usually saves me a lot of time using this form as opposed to the second one. Okay, so these two, numbers 2 and 3, I use those whenever I've got something written as r of t equals. And which form really comes down to what are those component functions. Okay, so then that leaves this last one, the one that we just developed. And that one, I use that whenever I have y equals f of x. If I don't have y equals f of x, I don't bother. I use one of the others. Because think about it, if I don't have y equals f of x, first of all, it's only going to work if r is 2-dimensional. And then if r is 2-dimensional, I have to end up doing a parameterization. I mean, I have to eliminate the parameter, which means I got to solve one of the components for t, plug it into the other. You may remember doing that back in the day. And that's way more work than I want to do. So it's all about being lazy. It's all about doing the least amount of work possible, which means just use whatever form they gave you and run with that form. If you have to change the form, you're spending time you don't need to spend, right? You're expending effort that's not necessary. So the first one is if the form is parameterized in terms of S. Parameterized in terms of T, it's one of the second two. And if it's y equals f of x, use the third one. So hopefully that answered your question, Bradley, but that's my kind of thought process.
Yeah, it does. So just do whichever works easiest.
Yeah, that requires the least amount of work.
Yep, sounds good.
Basically, you want to be like the universe. The universe is all about minimizing energy. For those of you who've taken physics, you've seen that, right? Everything's about minimizing energy. Be one with the universe, man. Don't fight it. Don't fight it. As you guys know that have studied thermo with me, entropy is a horrible thing because then you just start going, meh, life is meaningless. You become really nihilistic.
Yeah, you do.
That's the trap of learning thermodynamics. What does it matter? Everything's just going to end up being just some sort of a, boring hodgepodge of nothingness.
So did you hear what NASA did a couple days ago?
Maybe.
So they took some data from the Chandra X-ray telescope and the Hubble, and they were observing the galaxy, like the center of the Milky Way, and then the pillars of creation, the nebula, and they turned it into sound. The data.
Nice.
I don't know how they did it. It sounds weird. It sounds really weird.
The music of the universe.
Yeah, it's kind of creepy, honestly.
Well,
yeah.
the way they would have done it, I mean, you can easily assign tones to numbers. You just create your scale and then do the conversion. What exactly they use to correspond to different frequencies, I don't know, but that's kind of cool. So now you can listen to the music of the universe.
Yeah. Strange.
Is it dark and depressing?
The one of the galaxy was, for sure. It's kind of creepy. Like, it reminded me of some X-Files stuff.
All right. Which it probably should, right? All right, well, let's talk about what this curvature means. Like, what does K tell you? And in order to do that, I need to first introduce you to another thing. And this is called an osculating circle.
Osculating?
Yep. Not oscillating.
Okay.
Osculating. Okay, or sometimes it's called a circle of osculation. But yeah, so it's the osculating circle. All right, so what is this thing? Well, it's the circle of best fit. So if you were to imagine a curve, I probably shouldn't have erased that cosine curve, but if you've got some sort of curve, let me just draw one here. At any point, you can kind of fit a circle of best fit, right? So like for this one, pretend that this thing that I'm drawing right here is a circle. So that locally on the curve, like very close to this point, it's your best fit circle. If I were to come out over here, for example, on this point, that circle now is going to be opening upward. It's also going to be a little bit bigger. But again, squint your eyes so that that's a circle. So these are osculating circles. So this is the circle that best fits / approximates the curve. So it's sort of the equivalent of tangent lines, right? A tangent line is a line that best represents the curve at that one point. The osculating circle is the circle that best represents the curve at that point. Okay, so that's what the osculating circle is. Now, I want you to notice something here. Already you can see something that's different about the oscillating circle depending on curvature. Right, I had two different points on my curve. Which one has a bigger curvature, do you think? The green with the smaller circle or the red with the bigger circle?
The green one.
Yeah, it looks like the curvature is probably a little bit greater with the green. And there is a direct relationship between the curvature and the radius of the circle. All right, and so that's why this number, it's not come out of nowhere. It's definitely based on something physical, and it's the circle, okay? And so it turns out that the radius of the circle, it's actually the reciprocal of the curvature. So as curvature goes up, the circle for the best fit gets smaller. Yeah, so the larger the K, the smaller the circle. And similarly, the bigger the K, or sorry, the smaller the K, the bigger the circle. Like, play it out. Let's say we're getting really, 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 really straight. So we're not quite at a line yet, but let's just imagine we have something that is fairly straight. So let me draw something here that's just got a slight bend. Okay, so it's fairly straight, but has a little bit of a curve to it. So now if I were to try to fit my best fit circle here, it's probably going to follow the curve for quite some time, right? And in fact, this is so big that I couldn't even fit it on my whiteboard here. So this relationship really helps you see what curvature is about. It's telling you how big that osculating circle is. So go back to some examples that we saw, like with cosine. Remember what we saw with cosine? The greatest curvature was when we were at peaks and troughs, and it was a curvature of 1. So let me draw cosine here. I'll try to do a fairly reasonable job of it. Okay, so there's my graph of cosine. So we saw that the curvature was 1 when we were out here, right? So K equals 1. So that means that the best fit circle here is going to have radius 1 over that. So the radius is going to equal 1. Well, think about a circle of radius 1. From here is going to be at the origin. So the unit circle, turns out that the unit circle is the best fit circle to cosine when we're at 0. Another reason cosine is very, very cool. Yes, I agree, Victor. Like, it's pretty incredible how all this stuff kind of ties together. And so this circle, well, copy it. There's going to be another one that best fits when it's in the trough, another one in the next peak, and so on. But if we were to start moving away from here, our curvature starts going down, right? Remember that we get to a point of curvature of 0. Along the way, we're going to end up with a circle whose radius is bigger than 1 because it's flatter. What did we find for x squared? Y equals x squared. 1/4? I don't even remember anymore.
So the K equals 2 divided by the square root of 1 plus 4x squared cubed.
Okay, 1 plus 4x squared, thank you. So it's 2 over the square root of 1 plus 4x squared, and the whole thing cubed. Okay, so let's think about the parabola. So we go back to the y equals x squared. So at x equals 0, we saw that the curvature was equal to 2. So that means that the radius of the circle of best fit is 1/2. So if we were to draw that one, when we're at the vertex, so here's our parabola, that best fit circle is going to have a radius of 1/2. So this is 1, let's say. That would be your best fit circle. So it's smaller than the one for cosine, which tells us that the turnaround at the vertex of a parabola is tighter than that at one of the peaks or troughs of cosine. So I hope this helps give a little context to the k value, because sometimes when we just come up with these numbers, we're like, oh, hey, the determinant is 4, and you're like, okay, great. So who cares, right? This one though, oh, we get a k value of 6. That immediately puts into your head, oh, the osculating circle has a radius of 1/6, so it's a tiny little circle, which means it's a tight curve. Right. So that's kind of where that all plays out. And if you recall last time when I talked about n, that principal normal vector, we know that principal normal vector always is pointing towards the center of these curves. So it's actually pointing towards the center of these osculating circles. So I'm going to put that down on the list here under where I wrote radius. We also know that n points toward its center. So if you ever want to actually find the osculating circle, we know how to do it. We could even get the equation of it, because we know where to go, we know how far to go, and that'll get us our center. So let's actually do that. Let's take a function and let's find an osculating circle. Let's actually find the equation of an osculating circle for it somewhere. All right, so let's try something. Let's do a function we've not done. Oh, this will be fun. How about, let's go with f of x equals e to the x. And let's find the osculating circle at x equals 0. Okay, so you all know what y equals e to the x looks like. We're just going to see if we can find the circle of best fit when we're at the point x equals 0. All right, so that means we got to find curvature. So which of the 4 forms of curvature do you want to use?
The last one.
All right, thank you. I was about to say, if anybody says the first one, I'm going to figure out a way for my pen to teleport through and hit you as I throw it at the screen. All right, so let's use that last one. So we need to get y prime, y double prime. Well, since y is equal to e to the x, y prime is e to the x, y double prime is e to the x. Nice and easy. E to the x is always positive, so we don't even have to worry about absolute values. So our curvature is going to be e to the x over the square root of 1 plus e to the 2x quantity cubed. All right, so we all good with that as our formula for curvature?
Yeah.
Okay, so just notice a couple things. As e to the x gets, or as x gets small, right, goes to 0 or goes to infinity, you can actually kind of see what's going on here. Kind of look at what's driving things. On top, of course, we've got e to the x. On the bottom, it's like e to the 2x, the square root of that cubed. Well, the square root of e to the 2x would be e to the x. E to the x cubed is e to the x, e to the 3x. So this behaves a lot like 1 over e to the 2x. And so what we can see there then is that as we go towards infinity, let's say as x goes towards infinity, this curvature, we get something really, really big on the bottom, and the curvature goes towards 0. Well, yeah, as you're cruising up on that part, it definitely starts flattening out. But even more, if you go towards negative infinity, this still gives you basically 0 on the bottom, right? And so it also flattens out. So it's kind of cool that it leads to being flat in both directions, which it does, right? But let's look specifically at what we're finding. We're finding the oscillation at x equals 0. So if we put that in, we're going to get k is equal to e to the 0 over the square root of 1 plus e to the 0 cubed. So that's a 1 on top. On the bottom, we're going to get the square root of 2 cubed. Right? Because e to the 0 is 1. So this is 1 over 2 root 2. And we can leave it like that. You could leave it as 1 over the square root of 8. You could rationalize it, root 2 over 4, right? I don't really care. It's all good. But that's our curvature. Okay, so now then, what we know is that the radius of the circle is 1 over this. So we just flip this over. So the radius of that circle is 2 root 2. All right, so if you think about what we need to actually get the equation of a circle, you need two things. You need to know the radius. Okay, well, we got that. What else do you need to know?
A point.
Not just any point, which point?
Center.
The center. So if we can figure out where the center is, then we're good to go. All right, well, this is where big N is going to come in. This is where we're going to use N to help us out. So let's think about, first of all, let me just draw the picture of what's going on here. All right, so we've got e to the x, good old exponential function. Looks like that. We are at x equals 0, so that's this point right here, 0, 1. And so we're trying to find the circle of best fit. So we already know that it's going to be up in here, right? It's going to be up and to the left. We know its radius is now 2 root 2, so I'm going to go 2 root 2 away from this. I just need to know which direction. And that's where we're going to make use of N. Okay, so how do we find N again? Do you remember?
So the magnitude of t prime divided by something.
There you're going curvature. It does have a prime in it. It also has a magnitude of t prime.
So t prime divided by the t prime divided by the magnitude of t prime.
So n is t prime divided by the magnitude, or sorry, yeah, t prime divided by the magnitude of t prime. So in order to get that, we got to get t, and t, of course, was r prime divided by the magnitude of r prime. But we don't have r like we're used to. We're going to create it. I'm going to erase curvature stuff. Let me just write a piece up here. That r was 2 root 2. All right. So first things first, this is only two-dimensional. So we don't have to worry about a z component. I mean, if you want, you can put a 0 in there. I wouldn't bother. So instead, here's how I'm going to create my r. I'm going to parameterize it the same way we did when we developed that curvature formula. I'm going to let x equal t and y equal e to the t. Just change it from x to t. So now we can get these things. So r prime is 1 e to the t. The magnitude of r prime is the square root of 1 plus e to the 2t. So then t, the unit tangent vector, is going to be 1 over the square root of 1 plus e to the 2t, e to the t over the square root of 1 plus e to the 2t. All right, so there's our t. Before we find n, let's just look and see what this is when x is equal to 0. Because if x and t are the same thing now, x equals 0 is the same as t equals 0. So at x equals 0, this tangent vector is going to be 1 over root 2, comma, 1 over root 2. So that one, the x and y coordinates are the same, which means it's going this way. So t looks like this. And that should surprise absolutely none of you. Because think about the derivative of e to the x is e to the x. When we plug in 0, we get 1. So we know the slope of the tangent line is 1. Well, yeah, that's the slope of the tangent line. It's got that kind of a vector. All right, so now we got to find n. Before we even calculate it, you know where it's going to point. It's going to point upward. You know that it's going to be orthogonal. So that's what n is going to look like. So those are at a right angle. But let's see if we can figure it out. All right, so we got to get t prime. All right. So t prime, differentiating. This first one, let's think of this as a minus 1/2 power. So you get minus 1/2, 1 plus e to the 2t to the minus 3/2 times the derivative of what's inside, which is a 2 e to the 2t. So that's that guy. And then for the other one, we need to use the quotient rule. So the derivative of the top times the bottom, so e to the t times the square root, minus the derivative of the bottom times the top. Well, the bottom is a 1/2 times 1 plus e to the 2t to the minus 1/2 times 2 e to the 2t times the top, e to the t, over the bottom squared. So I'm pretty sure my derivative is right there. If I made a mistake, if something's incorrect, well, find it and correct it. But I hope it's okay. And then, of course, at this point, we need to go ahead and find the magnitude and then divide by the magnitude and then plug in t equals 0. And then we got it. But I don't want to do that. And I don't think you guys do either. In fact, you probably didn't even want to go as far as I did right here. And here's, let me just share you with it. So here's a little tip from Bruce. Now, be careful with this one. Okay, be careful with this one. If you don't know exactly what you're doing, you mess up. Okay, and then don't back to me and be like, "Well, right?" You gotta pay a lot of attention to this one. If you're in the plane, so in this case, when you're in the plane, don't try to do this if you're in 3D. If you're in the plane, there's a much faster way to find a normal vector. Much faster. All you have to do is swap the coordinates and make one of them negative. Okay, so to find a normal vector, take your tangent vector, swap the coordinates, make one negative. Let me show you with another example real fast. So like, let's say we had 1, 3. Let's say that this is a, it's not a unit vector, but let's just say that's a tangent vector. Then a normal vector, you swap the coordinates, 3, 1, and you make one of them negative. You change the signs on one of them. And I just realized you can't see that through the glare. Hold on. So again, t is 1, 3, n. You're going to swap to make those 3 and 1, and then change the sign on one of them. So I know there are probably some questions on this, so just give me 1 second. First, why is this giving us something that's orthogonal? Well, think about dot product. We know that two vectors are orthogonal if their dot product is 0. By swapping the coordinates, we're making it so that each one is being multiplied by the other, and alternating the signs on one of them makes it so that they have opposite signs. So when added, go to 0. Okay, so that's the first thing. Like why this works is just, it's the nature of the dot product. So you can swap them and then change the sign on one. But a second question, this is actually a more important question, is switch the sign on which one? Because like I switched it on the 3, so I had -3, 1. But I also could have, so I'm going to put here an or, switch the other one, right, where it's 3, -1, because that is also orthogonal. It just points in the opposite direction. Okay, so we have to know which one. And the principal normal vector is only going to be one of them. So the way that you tell is by going back to your picture and figuring out which way it's going to point. Let's look at our specific one with e to the x. So we had found that t was 1/2, or sorry, 1 over root 2, 1 over root 2. So if I want my n, I'm going to swap those. Okay, well, since they're the same number, I swap them. I'm going to make one of them negative. So the options are the first one or the second one. So my n vector is going to be one of those two. promise you. All right, so how do we decide which one? Well, look at our picture. Think about what these are saying, right? The minuses are telling you to go in the negative direction for those components. And the positives are telling you to go in the positive direction for those components, right? So thinking about this, do we want x to be negative or positive for this vector n?
Negative.
Negative. We want it pointing to the left. So what I know is that my n is actually the first of those two options. So this is a nice little trick when it's two-dimensional. Only two-dimensional, right? Only when it's two-dimensional. And be very careful, because it's very easy to mix it up and have it pointing the wrong direction. But you can probably see why I wanted to share this with you, because it's crazy fast compared to differentiating, finding the magnitude, yada, 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 yada. Okay, so if you're ever in the 2D world, which we often are, it can be a lot faster finding n than going through the whole.
Only works in the XY plane.
Only in the XY plane. Well, you can do similar things if you're in the YZ plane or the XZ plane. It's a little bit harder to visualize, but yeah, only works if you're in a plane, and primarily it's going to be when you're in the XY plane.
Okay.
All right, so now we know where to head to get to the center. We want to follow the vector negative 1 over root 2, 1 over root 2.
So I just want to make sure
Yep.
this normal, the one you circled, the n equals.
Yep.
We would have gotten that had we had plugged in values for that t prime.
Correct.
That's
if you gone to that t prime, plugged in 0, and then it may not have given us this exactly.
Yeah.
But once we
something
divide by the
equivalent.
magnitude, then it would have given us that.
That's
Yep.
crazy.
Yep. So you're welcome, by the way. You're welcome for this huge time saver. But be careful. With great power comes great responsibility. Be careful. All right, so let's kind of recap where we are. So we know we need an r of 2 root 2. We know that we need to go in the direction of minus 1 over root 2, 1 over root 2. And we need to start from the point 0, 1. Okay, so how do you change the length of a vector?
Scalar multiplier.
Okay, so you multiply by a scalar. Specifically, you multiply by the length that you want. Okay, so if we want to go in the direction n, but we want to go this distance, we're going to multiply those together. So let's take r times n. So we're going to take 2 root 2 times minus 1 over root 2 comma 1 over root 2, which gives us negative 2, 2. So this will take us the right distance in the right direction. And so if we want to find the center, all we have to do is take that we just calculated for how far we want to go, and we're going to add it to the point from where we were starting. which in this case was 0, 1. So the center of this osculating circle is at -2, 3. So it's actually really straightforward. Once you have these numbers, r times n, add it to your point. Done. Of course, we have to find r and n and all that, but notice that it's just a procedure. It's actually not that bad. And so now, given all this information, here's the equation of that circle. The equation of that circle is going to be x plus 2 quantity squared plus y minus 3 quantity squared equals 8. And the 8 is our 2√2 squared. And I apologize, I keep running in there. My phone keeps popping up notifications that blocks my screen. It's really starting to piss me off today. I need to tell these people to quit texting me. All right, but there is the equation of the osculating circle for e to the x at that point, x equals 0. So if you're ever interested in a circle of best fit as opposed to a line of best fit, this is how you would do it. All right, so how do we feel about the osculating circle?
That's a lot.
Yeah, it's a lot.
There is a lot, and it's bringing back a lot from algebra. But hopefully you're seeing, like, we're going in the direction of n. How far we're going depends on the curvature. So that's why we had to find the curvature along the way. All right, so I just want to share one more thing with you before we call it a day. I want to give you one more vector. We've seen big T, so the unit tangent vector. We've seen big N, the unit normal vector. Well, there's also one that we call the binormal vector. And we're going to use big E for that one. So look at the name and it will tell you a lot. It's a vector, obviously. That's binormal. So what does bi suggest in terms of prefixes?
2.
2, right? So this is a vector that's normal to two other vectors. Specifically, it's a vector, it's a unit vector that is normal. So orthogonal, perpendicular, however you want to think about it, is normal to both T and N. So T points in the direction of the curve, N is orthogonal to it, is normal to it, pointing towards the inside of the curve, but B is orthogonal to both. Okay, so how can you get a vector that's orthogonal to two other ones? Good, yeah, you cross it.
Cross product.
So B is defined as T cross N. That makes it binormal. All right, now I'm not going to bother doing a calculation and finding one because I know you know how to do it, right? You know how to find T, you know how to find N. I know you know how to do cross products. So instead, I kind of just want to talk about why we care about this and what it matters. So let's even just go to that example that we just did with e to the x. And so we've at x equals 0, so at the point 0, 1, we had found a t vector. We had found an n vector. So where is B going to be? If it's orthogonal to both, where's B going to show up?
It's either going to go
Sticking
into
out
the
of the
board,
paper of the board.
yeah, or out.
Yeah, so it's either going to be going into or out of the plane. So, right, in fact, we know which way it'll be using the cross product and the right-hand rule, right? T crossed N, my thumb is coming towards you, right? Or put your palm in the way of T and curl towards it. So B is actually going to be towards you or out of your paper. In this case, the positive Z direction. But this is where B is going to be. All right, so what do we hear about that? Well, check out what we have now. We have 3 unit vectors that are all orthogonal to each other. You have seen that before. Where have you seen 3 vectors that are all orthogonal to each other that are units? So Victor just said with a plane. You kind of saw this third one with a plane. You definitely saw the vector coming out. But specifically, a set of 3 unit vectors that are all orthogonal to each other. How about I, J, and K? What this does, if you include B with T and N, you form a rectangular coordinate system. Okay, yay, big deal. Well, think about it. So if we're talking about a particle that's moving along a path, these guys, T, N, and B, create like a moving coordinate system. So that if you want to set things up relative to a certain point in a certain path, you've already got your coordinate system. It's a really natural way to get those so that calculations end up being super, super easy.
That's pretty cool.
So that's the whole point of this B. Yeah. So again, imagine that you're studying astrophysics, right? And we're looking at the path of some comet floating through space. This is a built-in coordinate system that's moving with them, which you can imagine is really, really useful in lots of situations. All right. Well, I think we're going to go ahead and call it a day here. So let me just kind of pop into screen and say hi. All right. So think about where we got today. Oh, and by the way, you like the shirt? Starry Night, but with Boba Fett.
Yeah, it's awesome.
Millennium Falcon. That's good stuff. So think about where we are now. So we've kind of beat curvature to death. You now know everything there is to know about how functions are curving through space and space curves work. We've been able to now create coordinate systems for them. We can find these best fit circles. We have an idea of what curvature actually means. We've got formulas for all the different forms. We're pretty good there. So what we're going to do next time on Friday is we're going to dive into using it. And specifically, we're going to look at accelerations. We're going to look at finding tangential accelerations and centripetal accelerations. And for those of you who've taken your physics, after today or after Friday, you're going to be going, how come we didn't know this? How come we weren't told this, 2 quarters ago? And of course, the answer is, well, you weren't ready for it mathematically, but it makes it so that everything is super nice and easy there. So, but also to remind you, our first quiz is on Friday. If you go to the assignments, you'll see it there. Right now, it won't be available because it doesn't turn on until 1 o'clock. But at 1 o'clock, it will turn on. You'll be able to see it so that you can download it, print it, just work it out on paper, whatever. But then you need to upload it and submit it through Canvas. Please use a PDF. There are a lot of PDF converters for phones, a lot of apps, like I use one called Cam Scanner. You take a picture and then it just makes a PDF. PDFs, that file form is a lot better for me than others. If you are having trouble with that, for this first one, for sure is not a problem. You can just send me a JPEG, right? Or, whatever other kind of file. But we're going to need to get to the point where we're giving me guess. Anyway, so it will turn on at 1. It needs to be submitted by 1:40. Don't push it, because at 1:40, the system will time it out and you won't be able to submit it. Okay, so I'll get to that in a second, Seamus.
So make sure that you submit it. It shouldn't take you 40 minutes. It should take you like 20, 25. I build in that extra time to deal with any technological issues, okay? In terms of what it's gonna cover, it's not gonna cover the stuff we talked today. It's not gonna cover curvature. So it's gonna be the sections on vector valued functions. So being able to take limits, differentiate, integrate, find magnitudes, you know, all that good stuff. I forget what section that was. Let me just look at my book real quick. I don't even know what section we're in right now. So it'll be sections 3.1 and 3.2. Okay, so that's what this quiz is going to cover, sections 3.1 and 3.2. So do that, make sure you get the quiz done, and then we will start up class at 1:40. We'll be back in here starting at 1:40, and that's when we'll look at applying what we've been doing here in terms of N's and T's and curvature and whatnot. All right, so any other questions before we call it a day? All right, well, it was good seeing everybody, and I will see everybody on Friday.
See you, Bruce.
Have a good day.